Okay, I think let's get going. So welcome to today's talk. This is the latest in a series of talk as part of Bringing to STEM from the Faculty of Engineering at UCL. Today we have Dr. Alex Leung with us and Dr. Peter Lee, who will be talking about seeing inside metal 3D printing with X-ray vision. So I'm Rosie, I'm the communications officer for UCL Mechanical Engineering. So I'm just going to do a couple of housekeeping things and then I will pass you on to our speakers. So the talk is being recorded. It will go online at a later date. For this reason, we'll keep cameras and microphones of participants off, but you will have the chance to ask questions. So if you do have any questions for the speakers, drop them into the Q&A box as we go through, and then we'll come to them at the end. If you have any issues, so anything with sound or technical problems, pop those in the chat and I will come to you. And that's everything for housekeeping. So I will now pass you over to our speakers.
Thank you, Rosie. I think to start off with, good afternoon, everyone. So my name is Alex Leung. I'm a lecturer from UCL Mechanical Engineering, and on the other side, you can see Professor Peter Lee. So Peter, do you want to just quickly introduce yourself?
As Alex just said, my name is Professor Peter Lee, and I really hope you all really think of great questions for us. One of my own daughters is 17, trying to figure out not just where she wants to do the course, but actually what course she wants to do. So it can really relate to any sorts of questions you have about how we're coming to UCL Mechanical Engineering and having really a career in mechanical engineering, what jobs it can lead to, what science it can lead to. Please ask those questions. But I'm going to hand you back to Alex, who's going to do a talk for the first half hour, 45 minutes.
Right, thank you, Peter. So I'm just going to share screen. Let me know when you guys see that.
Still not come on yet. Oh, there it's coming. Showing fine, Alex.
Okay, that's great. Thank you. So yeah, thank you for those who spend their valuable hours from 1 to 2 joining this virtual lecture series with myself and Peter. And today's topic, as mentioned by Rosie, is about seeing inside metal 3D printing process with X-ray vision. So let's jump straight into this. But before we start, I think it's probably good just give you a quick background between myself and Professor Peter Lee. We co-direct the Material Structure and Manufacturing Group at Harwell. We have about 16 staff, about 15 PhD students, and we work with lots of academic institutions and collaborators on a variety of different types of advanced manufacturing research. And today we're going to showcase some of the stuff both us and the students and staff have done in the past. I think it would be really good to try to, show you guys what engineering and science can do to improve industrial process. So a little bit, additional information. So we are actually, a lot of us are based at the Harwell campus. So in addition to the Bloomsbury campus, UCL actually has at least 20 to 30 people working on this campus doing some very, very exciting research. It's about an hour away from London by train, 20 kilometers from University of Oxford. And we're based at this Harwell campus. You could actually visit the link below to find out more about this place. This place is very unique because it's got a lot of UK large facilities. So these really big instruments highlighted in here, including the Science Technology Facility Council, STFC, ISIS neutron source. We have a central laser facility, and we also have what we call a synchrotron light source. They're all situated in one single campus, which is unique in the world. So if you guys ever get a chance to go for an open day visit, I would strongly recommend you, as well as going to a visit to the Bloomsbury campus. Just a little bit more, European Space Agency and even the recent Vaccine Manufacturing Innovation Center is based on the same campus. So there is a lot of exciting research going on, be beyond 3D printing, including space, healthcare, etc., etc. So that's a little bit about the Harwell campus and our group. And we are based at the Research Complex facility at Harwell. As you can see, it's very close to these large facilities or instruments we use as a scientist to probe the heart of manufacturing process and products. So just to give overview of the lecture content to show, what is metal 3D printing, or in other words, for additive manufacturing, what sort of scientific challenges people are currently facing, and how does UCL mechanical engineering and other researchers come up with possible ways to overcome some of these challenges. And there will be some case studies and give you a brief or broad overview on the outlook for additive manufacturing opportunities. So first question, what is metal 3D printing? I think that's, it's probably one of the first technical term that comes up in the talk's title. I'm sure most of you are familiar with 3D printing of polymeric based materials, but let's see. So we start off with, similar to other AM or additive manufacturing process, you begin with creating an object using a computer aided design software, also known as CAD. You draw up a CAD model, then you divide the CAD into slices, what we call a digital file. So it's by sending this digital file to a process, so it could be a machine that that consists of, they use different type of feedstock materials. Some of them uses powder, some use wire, and some use metal sheets. The other aspect is we needed to use a heat source, and this heat source could be a laser beam, could be an electron beam, could be an infrared, a lamp. It could utilize what they call a photochemical, so basically absorbing light and convert into chemical reaction, or other type of curing methods to fuse these materials together to form a solid structure. And this process actually repeat layer upon layer, like what you do with Legos, like a building blocks, until you form this near nest shaped part as shown on the bottom right corner. So there will be some animation to help you to visualize that a little bit more later on. So there are actually 7 families of AM processes as a whole, which is, you can see them illustrated in these colorful pictures. If you want to find out more definition behind them, feel free to just go type on Google and type the ASTM 52900-15. You will find out a lot more information about what's going on behind the scene. Nonetheless, we can divide these 2 families pretty much into what we call so-called beam base, which is using either laser beam, electron beam to fuse the materials together as shown from the top 4, or the bottom 3 uses other methodology. And I guess most of you guys are probably familiar with the material extrusion, which is those typically you see in the mass market. So, and today we are actually mainly focusing on beam base, in particular on the laser-based additive manufacturing process. So let's look into what is powder bed fusion, because there are lots of technical terms, but I think animation would really help you guys to get familiar with the terminology. So we begin with the digital file again, but then we start to spread a layer of powder. We use a focused laser beam to fuse this powder according to the CAD file, and these processes repeat layer upon layer until we create this complex geometry. And in fact, this type of AM process is being used in a variety of different types of product application, from jewelry, aerospace, power and generation, structural commodities, biomedical, all the way to the marine engineering application. So there is a lot of things that could be used, but as you can see, most of these components are rather have complex geometries, and they're usually relatively small using the powder bed fusion process. What are the advantages, right, of using metal 3D printing of the AM process as a whole? Was, if you look at these 3 examples here, Well, first of all, we could actually customize the part we wanted to suit its application. As you can see from the Airbus 3D printed wingtip, it's rather obscure shape, similar to both the Renishaw and the launcher part for a rocket, and also on the far right. That's a really useful thing. It gives a lot of design freedom for engineering to optimize the structure so that you don't actually need many, let's say, subcomponent. You could actually build several components into one single part. So that would be really, really useful in terms of minimizing the number of production steps and hence the cost. The other thing really, really useful is of the flexible manufacturing route, because then it's actually, you can cut out a lot of the supply chain let's say processes, and then it will streamline the product development time, so you shorten the lead time of developing something for your customers. And another really good example is, if you think of, we can create a digital file in the UK, we can send it to Australia, Japan, or in the US, and then get the part printed without going through all these delivery, customs processes. So it would really be beneficial for some businesses. And you could see from during this COVID-19 pandemic, a lot of a company began to research and also try to utilize this technology for some of their products. Not all, but some. Right. The other thing is the in terms of production yield. That's a very, very important part, because you could traditionally subtractive manufacturing, like machining, you actually buy, let's say, 20 kilograms of titanium, only 1 kilogram actually goes on the aircraft, and they call this the buy to fly ratio. And this buy to fly ratio could significantly improve using AM up to maybe 1.5 to 2 to 1 ratio, which is really, really good. So these are lots of advantages. But I think lastly, what's most important is some of these powders is recyclable. So it means when you finish some of the build area that has not been selectively melted or sintered, then you could, some of them could be reused for the next or subsequent builds. That means this process can become very, very sustainable. So just wanted to give you a few things to take away from the presentation. So from an economic impact perspective, why lots of people are interested? As you can see, the market actually grew from 6 billion to 26 billion USD. That's a projection by a very, very well-renowned report in the industry called the Holler's report. So for those who are interested in reading more, feel free to just Google that, and you will find lots of interesting things. The other thing is it underpins, generate gross value added for the UK industry, and also support lots of jobs in general. So so there are quite a lot of incentive in researching, and taking engineering, and work in the manufacturing sectors in a long run. So the second question is, but why aren't we using this more, right? If it all sound very, very beneficial to a lot of industry. So here is the reason why. The industry itself faces quite a lot of scientific challenges across what we call a value chain, from design, powder management, production, all the way to end use. Here, I just want to highlight some of the things that industry is currently facing. So if you look at the part on the left, these are just test geometry. You can see the green is the CAD part, and the gray is actually the actual build part that has been scanned, and we visualize it digitally. You can see there are some deviation at certain elevated angle. You're unable to actually produce something that is representable or usable for the end application. So from a design perspective, there's a lot of thoughts. And this process, because it's used a heat source and it cools, the heating cooling cycle sometimes can arise some forms of stress. We call this as a residual stress, and this can exceed the strength of the material and causes delamination, and that means we can't actually build the part anymore after a certain number of layers. And the other thing is how we can actually keep the powder to a level that we don't have any oxygen, because oxygen could alter the behavior during melting, and it may lead to some other phenomenon, which we're going to show some stuff to you later. So stay tuned with the presentation. And the other thing I mentioned, we're using a very, very high energy heat source. It doesn't just melt the material, it also can cause vaporization, which means you alter the chemistry of your part, and hence the performance will always change. And that also lead to a variety of different type of what we so-called imperfection. Do bear in mind, not all parts consist of that, because we're scientists, we're trying to, an engineer, we're trying to help industry to tackle some of these things they come across, and we just gather all of these pictures together in one schematic to show what sort of imperfection it can be formed. But how they are formed is still not really well understood, and which is why we need next generation engineers like you to help us to come up new ways to characterize them. So all in all, you can summarize everything pretty much in one single sentence, which is the process structural property relationship. And there are many different types of tools can help to tackle these challenges. You could use a virtual simulation. So you could sit in front of the computer trying to come up with theories and how, this powder spreading process, the melting process, and how material solidify, so changes from liquid to solid, all the way at the component level. You can simulate that, okay? And the other thing is material scientists, engineers, trying to use, let's say, microscope to look at these powder, look at the component, look at the weld, and also some will use large facilities like big instruments to probe the internal structure of the part to actually get some additional information about stresses, about size distribution of these internal grains. But anyway, just treat it as internal features. But there are two more profound questions. As a scientist, we always ask questions. Have they actually included the right physics when they were doing the simulation? Okay. And the second thing is, these process actually takes place relatively fast. Can we actually get real-time information to help verify or validate these virtual simulation results? So that, both things goes hand in hand. So this is some of the things that we're going to talk a little bit more as we go along. So the process structure property is all governed by the process actually at the beginning. And all of that from powder to the solid track, you saw in the very first video, actually, it only takes less than 1,000th of a second, which is really, really fast. All of these things happen within that time period. We really wanted to find out why, and it's very, very challenging. So this diagram looks very, very busy. Don't worry too much about this. It just shows microscopically what does a melt pool looks like, but just focusing on these pop-up yellow boxes. So first of all, we have the laser beam interacts with matter. That could be the powder, the liquid, the vapor, and so forth. We also have ejection of materials happening during this process. We have fluid motion. So for those who are interested in physics, engineering, fluid, it could be a gas, it could be liquid, there is lots of things happening. And there is a solidification phenomenon, which means from liquid to solid, and then we form the structure we're interested. So just, these four things itself is already very complicated. So we want to know how and why these things happen. So how do we capture these processes or phenomena? Well, I give you guys a hint earlier at the beginning of the title of the talk, which is something related to X-ray. As you can see, these two hands, you could already can imagine X-ray has the ability to penetrate through objects, and we can use attenuation of X-ray, which means that some of the X-ray will be absorbed, some of the X-ray will be arrive at the camera. We use these images to help us to see what's going on inside the process, which is a very, very powerful technique. But what's so different between the X-ray generated from hospital, let's say a CT machine, to a large facility, is you can just simply imagine a camera that and a light source. The more light you have, the fastest you can capture the image with less exposure. So that's the reason why we need a lot of light. So I'm going to give you guys a little bit more information. So now taking you guys to the diamond light source, there is a really beautiful YouTube video showing the electron is accelerated towards the speed of light through the linear accelerator and the synchrotron booster. After that, the electron is ejected to this storage ring about 500, 600 meters long. And what happened is each of this end station, we use really powerful magnet to bend this electron. If you think about, if you're driving really fast in the car, when you turn, it will generate sound. In this case, it will generate light. And using this really bright light and coupled with different type of instrument, we could actually use this to non-destructively probing the process. In here, we're probing a forging process. So the purple bit is where the ramp and the material is based in the inside. So we can actually do 2D, 3D, and 4D imaging with that. Having the light is one thing, right? We talked about metal 3D printing, but we haven't really talked to you how we actually perform these experiments. So this is imagine an AM machine, and we have a powder bed within it, and we scan the powder bed. But during this process, we continuously to use X-ray to probe the process and collect a series of images. And we call this a process replicators. And we could actually do lots of things which involve with engineering, because we needed to remote control this using that allows us to do powder spreading, control atmosphere, and so forth. And we wanted to use the process replicator to help us to better understand that. So how does it work? So you begins with powder spreading. We have a light, laser rastering, and we have X-ray going through, as you can see. These are the images of a laser generated melt pool of titanium, and you can see the melt ejection really happening. The melt pool is forming. On the right hand side, you can see actually there is fluid motion. So we use this technique and apply that to different type of powders as well. So we're looking at oxidized powder versus virgin powder to see, because powder quality is absolutely paramount. And you can see with increasing amount of oxygen, it changes the depth of the material. It actually creates more imperfection, and these could be detrimental. So there is actually a growing field in understand at which point the powder should be recycled, at which point the powder should be scrapped, so that we don't see what you observe at the bottom part of the images. So what you can see here, the powder is actually on the right hand side in my cursor. The middle, the black really dark bit is the melt track. So there are many other things you can see using other type of imaging. You can see the black dot appears on the left-hand side is an optical imaging. Now you're looking at the surface of the powder bed, but we don't actually know what's happening underneath, right? Which is why we needed to use the X-ray imaging technique. What you can see is during this multi-layer build, sometimes you get this really black droplet just flying out towards in the middle of nowhere. And if we do a zoomed in, what you can see is actually, if there is a pre-existing void and this void contains gas, when the laser is heating that gas up, it causes this ejection of liquid. And that explains why you get this droplet formation or possible mechanism. But whereas traditionally, if you only observe at this melt surface, you won't be able to get this better understanding, which is why this technique our group has been champion developing is really, really powerful. So there are many other things you can do. You can actually look at the morphology of the laser generated cavity during the process. You can also see how voids are forming, highlighted in red if you look on the far right. And we have a team of researchers are studying how these bubble formation process to trying to come up ways to mitigate that. So we also have students have been looking at finding out, when you're spreading this layer of powder within the machine, what if you are changing different parameters? How does that actually influence the imperfection formation? As you can see on the top left corner, increasing the power under the condition study, wow, dramatically actually influenced the imperfection formation, and these voids could cause some troubles further down the line. So there's lots of research that's been going on behind the scene. So observing these processes is one thing, but we also work with collaborators from Australia and others to try to come up with ways to mitigate some of these voids and cracks within the powder materials. So we're trying to add some additive onto the powder surfaces, or even pre-alloy them in the melt, so that we could potentially reduce the formation of these imperfections. So what other things we could do using these images? As you guys probably know a lot about Google cars, some of you may have seen it. They actually use image quantification to track human or cars, vehicles, or other things moving. We could actually do something similar here. So beside engineering, material science, we also need to learn a little bit about computer science. So we could actually track the formation of these melt features, including the dimension, the shrinkage properties, and so forth. We can also do tracking the fluid velocity, tracking the kinetics behind the pore as it's being processed, and also tracking these ejection of materials and all of those things. Why do we want to do it? Because we wanted to gather all of these responses, because it involves with data science. We can actually feed this data into the process simulation to actually help them to verify what's going on, and also maybe help developing new ones to progress the technology. So there are a lot of interesting, exciting things our group and UCL is doing as a whole, beside understanding, because we look through the surface of the melt features in the 3D printing process, and we also combine them with the X-ray imaging. All in all, we wanted to help industry to develop control algorithm to mitigate these imperfection and defects. And we work with lots of people to do that. And we also combine with convolution neural network to help us to develop models to predict porosity within the part, because we find this is a very useful things to understand the build quality behind the process. So that's further moving towards how to use computer science to help. And we use the X-ray images as the ground truth, and we use the machine learned model to help us to predict. But most importantly, we can also converting these 2D images we collected from during the build process and build it up as a 3D. And using these ideas, we could actually pinpoint where the, let's say, location-specific defects. And from that, we can create another digital file. And using that digital file, we can use it to predict individual component lifing of of the part that is just been built. So even within the single build, you can now say, oh, this part could use for 25 years, this one can use for 24.5, or this one can use only for 10 years, because we've tracked this manufacturing process all the way along. And this is a growing topic about Industrial 4.0. So for those who are interested in pursuing a career around that, look this up. So all of these things is about predicting component lifing, right? And optimization of the process. So in summary, I think it's bang on around 30 minutes. I hope we give you an overview of what AM could offer for in terms of a wide range of industry, what type of technical challenges people are facing, and how the UCL team working collaboratively with lots of people using multimodality imaging to capture aspect of the process. We still have a lot of things that we would like to understand and better improve. And of course, I mentioned how we use providing real-time data combined with some of the emerging data science tools. We can help understand, develop, and validate existing simulation models, or even help progress the next generation. And all in all, is we wanted to really help the end users to apply the above tools and the things I mentioned, the X-ray, the imaging, the image analysis, the big data analytics, to help develop new strategies to build the part quality. So these are the key takeaway from this. But I think I just want to finish with the two slides on the outlook, right? So what's really happening? So far we've drilled so deep into a minute scale in micron resolution at really high speed. I forgot to mention those images are taken up to 40 kilohertz, so they're in microseconds regime. So very, very, very fast and high speed. So if you think about it, what's happening is Deloitte Insight made a really beautiful diagram to show what they imagine the 3D printing process or metal 3D printing process looks like. You design your part in the blue area, you can perform some simulation, but at the end, when the part is being manufactured, so in the red region, it relies on a lot of imaging or monitoring devices. It could be any sensing technologies to help providing the feedback and developing more useful data. And then we use that to verify and connecting the stuff that has been done in the blue region, which is the design and analyze aspect. So you can see all the way from design to end life, there is a lot of data is being transferred, between each of these 4 sections. So there is lots of information, lots of interesting things going on, and we are only looking at the middle part at the moment, which is highlighted in this region. So an outlook, there is lots of strategies across in the world, from the UK, which is the top 3. You also have Germany, China, America, Austria, European colleagues. They're all actually spending quite a lot of investment and to grow and progress this technology, because they see the benefits. So do watch out. This is up and coming, and hope you guys find this interesting and useful. So lastly, just want to use this opportunity to once again to thank. We have lots of students, postdoc, staff, collaborators to help actually deliver these research results. And we want to thank our funder from EPSRC, our Royal Academy of Engineering, and our industrial sponsor. And, and those large facilities gave us an opportunity to use these really beautiful instruments to do such research. So just wanted to say thanks again for your attention. We hope you enjoy the presentation, and now it's time to go for the Q&A session. So I'll stop sharing and let's read out some of the questions. So hi, Peter.
3 good questions there. I'm going to start at the bottom, which is, why is it called an X-ray radiograph if the ray is an X-ray? Like, what is the radio part? Well, radio is a Latin word. It actually comes from the origins of radio is radius or ray. And so it is radio, which is the same reason that you get X-rays causing a radiograph. That's why radio is in radio waves, knowing that an X-ray is actually something very high energetic wave. It has a wavelength of just a nanometer or smaller, all the way down to angstroms and the energies that we use, and can penetrate very deep through material, where a radio wave is at a much larger scale, really in the millimeters, all the way up into the many hundreds of meters are the radio waves that are used to propagate, well, for us to communicate around the world. So that's where it comes from. And the graph part is, as it sounds, graph comes from, I think it's Greek for the origin of recording or drawing. I think it's from drawing, but don't quote me on that.
Thank you.
The next question to Alex, if you want. Alex, do you want to do the why? So
limitation.
King Yang has also asked the limitation of 3D printing compared to, say, smart materials.
Right.
Do you want to do that?
Yeah, sure. Yeah, I think yeah. So first of all, these two terms I should use. They are they're completely different things. First of all, the limitation of 3D printing, depending on which families of technologies you're looking at, but most of them have a limitation in terms of the build size. So compared to traditional manufacturing like rolling technology or forging, some of the parts could be in up to 150 meters, but most of the parts that additive or 3D printing could make, so far as I know, they are less than 8 meters in size for metals. I know there is emerging technology for building concrete, a 3D printed house, so that's something different. Then in terms of smart materials, I guess the limitation. Maybe I should just probably talk a little bit about what's the definition of smart materials for some people. So smart materials are materials have multiple of functionalities, and these functionalities could really, let's say, once it sends, let's say, heat, and it will transform and do some other, it might expand or shrink, or it may generate electricity. These are also so-called smart materials, and these smart materials are have their specific use, and you could, some people do use 3D printing technology to make smart materials, but in terms of the limitation, I think probably yeah, I don't think we could really answer that because it's too broad.
It's also, exactly as you said, Alex, they're complementary. As you said, 3D printing is used to make smart materials.
Yeah. So
some of the things like smart cloths as a material that are used, functionality are 3D printed with a weave in it. And one of our PhD students that Alex and I are currently supervising is 3D printing smart sensors to incorporate into the material to go through. So, but really great question. The two techniques overlap in between 3D printing and smart materials. There's another question here from Leo, who asks, as a senior school student, I've been fascinated with DMS, SLS, so selective laser sintering, 3D printing for a while now, but learned about some of the issues which plague the technology. Most recently interested in investment casting for titanium pistons in the automotive industry. And I'm guessing, yeah, titanium pistons is a new one to me. I know lots about aluminium cast pistons and steel. To what extent would you call SLS 3D printing a lost cause? So I wouldn't call it a lost cause at all. Selective laser printing is really where you just take the powder and you don't fully melt it, you sinter it, and then you put it into a furnace and fully melt and densify it. It is actually being used in a lot of production. It's used right now to produce actually millions of bioimplants for joint replacements, for knee replacements, shoulder replacements. And it's also used for both selective metal laser sintering and also selective laser melting. It's used for direct printing of bespoke repairs. for something though, like automotive, let's just put automotive in context. A classic automobile costs on the order of about £20,000. How many components are in it? There's actually about 10,000 components in a modern automobile. If you come all the way down to all of the electronics in it, all of the fasteners, everything that you have in it, which means that each component sells for less than £2. So really, if you want to make something for automotive manufacturing, it has to be a fraction of that in the cost to make it. So SLS for automotive is probably decades away. But for things like biomedical, glasses even probably are very high value added, and definitely aerospace, it is there, and those limitations, and there are limitations to every process, are being overcome and it's being applied. So I think it's something that it still has real potential, and you'll be seeing more and more components made out of it. It is used by the automotive industry. It's used by the automotive industry to make test cars for crash testing, because doing something like an investment cast titanium piston takes half a year of development, and you need to get the car in a crash test a year before you actually finalize the design. So the components for crash testing are 3D printed, but when it comes to production run, where it has to cost less than £1 per component on average, it's not made by additive manufacturing.
Just further to Peter's comments about the crash test as a really good example, is because if you actually needed to create those components, it requires a new set of molds, and during the design iteration, you probably needed to keep designing and creating, buying, making new molds, and these molds actually cost quite a lot. So you can see the really great advantages of using AM or 3D printing technologies could significantly reduce the upfront costs, and you could quickly test the design of some of the components you're interested in using for an automobile or other transport vehicles. So there's actually quite a lot of really good advantages. But the second point I would like to make is, which is a common question raised by a lot of people who are new to the 3D printing industry, is we're not saying 3D printing will completely take over the other manufacturing technologies. In fact, it's supposed to be used as a complementary techniques. So there are things that will never be replaced by traditional manufacturing. So we just want to make sure we point this out and let you guys to think, there's another new technology out there we needed to learn, and that might bring potential benefits in a long run.
Okay, I'll do one, and then you can read one and do the next.
Sure.
I'll answer from an anonymous attendee. When talking about imaging, 2D, 3D, but also 4D was mentioned. How does the 4D bit work? Okay, well, so we have 1, 2, and 3 spatial dimensions, but we also have temporal dimensions. So we add time, and Alex actually specializes in adding chemistry. We can also add crystallography. We can add all sorts of evolution of chemistry into it. So in fact, when we talk about imaging, we talk about multiple modalities. One mode is the spatial mode, one mode is temporal mode, and then we go through to chemistry, infrared, and other things. So the 4D that Alex was talking about was actually adding time. So it's taking what is, imagine Superman had 2D vision in X-ray plus time. What we can do at a synchrotron is actually even better than Superman's vision. It's 3D imaging, so you can see everything in 3D over time. So we go a step beyond Superman. That's the way I like to put it. Alex, do you want to do the next one?
That's right. Okay, so I guess it's another anonymous attendee asked the question, can additive manufacturing be used to design more efficient car engines or new engines that run on more environmental friendly fuels like bioethanol? So I think I would like to maybe start just at the first part of the question first, about whether we can use that to design new engines. So in fact, there are quite there are at least 2 to 3 really good industrial case studies. For example, the GE fuel nozzles, that's one of them. The other one is what's shown in the presentation, which is the launcher made a copper component, rocket component. Why they could make this a more efficient engines? Well, first of all, Peter mentioned something very, very interesting. You know, there are over 10,000 components in an automobile, right? So if you could actually minimize the number of components by combining them, changing the design, and you can also optimize, let's say, the flow properties or structural properties, you can actually save weight. First of all, you can improve the fuel efficiency internally during the combustion, and both of these things will help reduce carbon emission. And by reducing carbon emission, hopefully we can make things more environmental friendly. And the other really good example I talked about the launcher rocket component is because about the design iteration. So it's the fastest way to make, probably one of the fastest way to make, you know, keep doing design iteration for these nozzle component without using traditional casting method. Then you can save costs, and hence, you know, if you look at the carbon emission as a whole in an entire process of making a final product, it's not just talking about the AM part. You also have to think about, you know, where does the materials come from, how does that combine with other products, etc. So hopefully that gives you a flavor or an answer to how AM can possibly use to design more efficient engines.
Just to add on to what Alex was just saying, that although we're not directly 3D printing engines at the moment, the engines are actually mostly cast. They're either now low pressure die casting or going more and more to high pressure die casting to reduce the cost. But in Formula One, and there's a number of Formula One companies close to where we're based in Oxfordshire, they actually use almost all their designs. They first of all design and 3D test the overall shape with 3D printing. But when they go to actually make the engine, most of the companies that they contract out to, what they do is they 3D print the mold that makes the engine. And the reason for that is going back to what Leo said, that the quality of the 3D printing isn't always as high as you can get out of a cast component, and especially not as high as you can get out of wrought component in many conditions. But making that mold, what they do is they'll make the bulk shape of the mold, and then they'll have the inner panels as replaceable, and they'll keep on reprinting the 3D printed for that. And what that lets you do is, instead of using something like Leo suggested, which is investment casting cools very slowly, and you get a larger, coarser, and less strong structure. If you cast into 3D printed metal mold, you cool faster, get finer grained, higher properties. And so that's how they're now making Formula One engines. I do work with Ford. Ford also are 3D printing, even for commercial, segments of their molds. Not all of the mold, but segments, again, for cost.
Thank you, Peter. That's really good. Really good insight into what automotive industry is currently using.
And I guess that's the next point. The anonymous attendee said SLS 3D printing has been used in Formula One for years now, and you're absolutely right. It hasn't been used to make the engines directly, as far as I know, to make the molds. It has been used for making lots of other components. And for sure, any component, when they first of all test it and do the test drive, is almost all 3D printed.
I think there is a question from Leo, another really good question. Since post-processing is almost always required for precision DMSLS, which is direct metal select laser sintering, printing parts, surface machining and support structure removal, how have you decided to overcome this fundamental flaw? Okay, so this is, I'll answer the first part first, and then we can talk about the support structure removal. So both of these two items are ongoing scientific challenges that you know, the industry is focusing on to solving. That's why there are a lot of original equipment manufacturer making these AM machines. They are focusing on utilize new type of laser technologies to help minimize some of the roughness of these machine part, or come up with different type of build strategies we talked about to minimize that. But in terms of support structure removal, that's a really good question. So this is most of the stuff are actually still in R&D phase. So what people have done so far is they have tried to preheat the bed. By preheating the bed, they slightly sinter some of the powder particles, so it makes it easier to melt from the component and away from the component onto the above the powder bed surface. So some of those are still relatively new technology that people are interested in developing, because by removing the support structures, it will massively, save time for the post-processing, and also it can mix more powders recyclable. So those are very good questions that we don't immediately have the answers. I think that's why we need you guys, the next generation engineers, to come to UCL and maybe help everyone to tackle them.
Okay, great. The next one was a point from an anonymous attendee that SLS 3D printing has been used in Formula One for years now, and it's in the chat that it's used for steering wheels, and they're absolutely right. It's been used for steering wheels, it's used for seat backs, it's used for complex shapes and junctions. It's used in a lot of the intake manifolds, which don't require quite the same properties as the engine requires. And there's propagating more and more throughout Formula One into different components that are actually on the road, or rather on the track. I think the next one, if you want to cover, which is on, I'll ask you the question, Alex. Yeah. I don't fully understand how machine learning is used to determine the component lifespan. If you could re-explain it, it would be great.
Okay, no, that's really good. That's a really good question. First of all, just want to clarify that the machine learning we talked about during the presentation is mainly for us to interpolate some of the results we've got. So for example, if we can see imperfection forming in the radiographs or in the images, we could use this information to actually estimate, or when you come to different process parameters, how will the build quality changes. So there are things we could do, but in terms of completely using machine learning for component living, I think we definitely need a lot more data to start off with. So we need to collect lots of different input variables from machine parameters, materials, properties, and all these things. And I think we are still many years away to completely using this technology to determine the component lifespan. But in contrast, okay, just reiterate for those audience interested in what we are proposing is, from these images we collected, because you can actually clearly see the position of individual defects in the little bits of the part we are trying to build. We can actually, during the layer by layer process, we can stack these 2D images and make it into 3D. And using these 3D images now, we can actually pinpoint the location of these individual pores or voids or cracks. And then we can further use data science to actually get some statistics information about this individual part, and then that could potentially, if we couple that with stress analysis, we can actually predict the component living, whether it's suitable for a certain application. So this is the vision, what we would like to deliver.
Okay, great. Leo has another question, which is, what types of metals have been cast into these 3D printed molds, and how are you able to withstand temperatures approaching 2000 degrees C? So most automotive engines and most components in an engine now are aluminium. And what happens is if you have something that you want to cast, oh, sorry, I've got this blurred, so only work is in front of me. So if you cast a molten metal into a mold, so this is the mold and this is the molten metal, immediately the surface of the molten metal will solidify and a small gap will open up, and the heat transfer will be controlled by that gap. And what happens is that although the metal may be at 2000 degrees, and actually the melting temperature of aluminium depends on the alloy, 550 to 630 degrees or so, the temperature of this will never go through and make the mold as hot. And the molds are water cooled. So you'll have a panel which is 3D printed, injected into a water cooled permanent backing. And the temperature of this will only get up to 400 degrees or so. That's still detrimental. The molds are printed usually in a steel. It can still cause warpage, which is also why they're made as panels and they can be replaced after a few thousand casts. So two separate things. Mostly it's aluminium that's used in those cases. There are 3D printing of other metals, and I guess with 2000 degrees, you're thinking of titanium, which is melts somewhere around 1500. And depending on the alloy. So you'll go through, and that's the one thing. The temperatures are usually lower of the metal. The second one is that the mold never gets that hot.
Okay, so Peter, thank you. I'm going to pick up the next one, which is, do you 3D print your components in inner atmosphere like argon or a vacuum to prevent reaction with elements in the air? Right, so that's a really, really good question. I would say depending on which AM machine you use, some of them are actually you can print things in air, but if it's metallic part, prefer not to, because as I mentioned about the oxidation problem. So you could actually use argon. You could also use helium, depending on which type of machines. And some people have begun to use nitrogen and a few other type of gases. The key thing is you can prevent reaction with oxygen in the air, but some researchers are actually thinking maybe you could utilize this reaction to do something else in the process to improve the efficiency. So that there's actually quite a lot of exciting research going on into looking into the type of gas and how you can manipulate the pressure of this gas to alter the behavior of the printing process.
Great. Well, that leads right into the next question from anonymous attendee on how are reactions avoided considering the high temperatures used. And it's exactly inside of a 3D printer, the laser pool heats the metal up, as Alex was saying, into thousands up to the vapor temperature and forms a plasma up to 3000 degrees. The reactions are avoided by putting inert atmospheres in. And as Alex said, argon's used in anything that's a steel because nitrogen is lower cost, but it actually reacts into steel and is picked up into steel. You get nitrated steels. So in any steel and in titanium, it's usually an argon atmosphere. As Alex was saying, nitrogen is used for some lower cost materials. It's not really detrimental in aluminium, so it's used if you're doing aluminium. And so the reactions are avoided by putting in an inert atmosphere there. And I think
we've reached.
I think we're almost out of time too. We finished our hour, Alex.
That's right.
Back to Rosie.
Yes. Thank you so much. That was such a good talk, and thank you so much for answering all of the questions. And thank you also to everyone who asked questions. They were really, really good, insightful questions. So that's great. So thank you again for coming. Thank you again to our speakers. This talk is part of a series called Spring into STEM from the UCL Faculty of Engineering. So do have a look at everything else that's coming up. I'll drop a link in the chat just now. If you're specifically interested in coming to talks from mechanical engineering, then our next one is next Friday. It is about robotics. I've also put a link to a feedback survey, which is completely anonymous. It'll only take a couple of minutes, and it just helps us that if we run this session again or sessions similar to it, it just helps us make sure they're the best that they can be. Thank you again to Alex and Peter for such an interesting session, and thank you again for coming. And hopefully we'll see you all at some point soon, either in person or online again.
Okay, thanks very much, everyone.
Thank you all.
Thanks.
Thank
Bye-bye.
you.
Bye, everyone.